Okay, off we go. So last time we were laying groundwork for Green's theorem. We hadn't really quite gotten around to actually being able to state the theorem. Reminder: the reason is if I just state the theorem without the context, without setting the scene, as it were, then it wouldn't make any sense. It would seemingly be this arbitrary formula we're writing down for no apparent reason. So quick reminder. What we talked about last time, we talked about this idea that boundary is now an oriented thing, right? So heretofore boundaries have been just curves. Now they are oriented curves, and very importantly, oriented according to a very specific convention. Arbitrary, to be fair, right? But standard for a very, very, very long time. So that is henceforth the word boundary means oriented specifically like so. Okay, next we talked about accumulation. This was just a kind of a refresher, really. I've used this idea of accumulation a lot throughout the course. Every integral we've ever written down, every integral you've ever written down in previous courses is always an expression that the whole is the sum of the parts. Right? And really an integral is just the process of capitalizing on that fact and chopping things up into little pieces and then literally writing the whole as the sum of the corresponding quantities on the parts. So some things accumulate, some things don't, right? And very importantly, we can't just go around assuming that everything accumulates and writing integrals to represent every little thing because you can't, right? Again, a nice, easy little example. Perimeter does not accumulate over areas. The perimeter of the whole is absolutely not the same as the sum of the perimeters of the parts. Right? So we got to be careful before we go around making claims about such. So now picking up here from last time. So turns out there is a really surprising accumulating quantity. And that is boundary circulation. Given some vector field, you have to have a vector field settled to be able to talk about what you mean by boundary circulation. But given a vector field, boundary circulation is an accumulating quantity. Now, it doesn't feel like it should be, right? So let's draw sort of a quick picture. Here is the domain on which we would compute the boundary circulation of the whole. Here is the domain on which we would compute the boundary circulation of the left piece. And here is the domain on which we would compute the boundary circulation of the right piece. It doesn't look like they're the same. After all, when we chop this region into pieces, let's see here. I will use orange for this. This edge right here is new edge on which we therefore have new terms in the line integrals on the left side of this equation that we're hoping might work out. Right? So doesn't it seem like it ought to work? Weirdly, though, it does. And the reason that it does, if you look at the sort of the suspicious terms, right? There's as part of the boundary of D1, I'm going to be moving along that orange curve, moving in the way that boundaries do with D1, the region whose boundary I'm talking about, on my left. As part of the boundary of D2, I'll be moving this way as boundaries go, moving in such a way that as I go that way, the region whose boundary I'm talking about, D2 this time, is on my left. Right? So these are what you might call the suspicious, problematic terms, right? If I want the whole to be the sum of the parts, this is the problem. This is what's making it not work, or this is what's making it seem like it wouldn't work. And the beautiful fact is, though, that these two extra terms, same curve, opposite orientations, which therefore have exact negative values and cancel. And so the problem just goes away. And even though it didn't look like it should, in fact, this has worked out and boundary circulation accumulates. Now, if you're concerned about the fact that we only chop this into 2 pieces, and maybe things get weirder if you chop it into a bunch of pieces. Let's look at such a scenario just real quick, and I'm not going to write down the notation for this because it's just bulky. Doesn't really serve much of a purpose. And if I have some region, right, with a boundary, oriented, of course, as boundaries are, namely with the region on my left. Right, so the boundary circulation of this great big monstrosity would be computed over this purple curve, oriented as indicated. But now, what if I instead were to look at the sums of the boundary of the boundary circulations on the parts? So, for example, let's look at this piece right here. Right, what is the boundary circulation on that piece? Well, I would need to compute line integrals on that edge going that way, that edge going that way, etc., etc. Now, what about on this piece here? Okay, well, again, following the rules, I would be computing on, let's see, that edge, and then this little itty-bitty edge, and then that edge, and then that edge. Right? And now let's look and see, did the cancellation that we were hoping for happen on this edge? Right? Among many other edges that we introduced when we slice this up into a bunch of little pieces, I've got a vector line integral term from the boundary of the blue side going upward. I also have, as part of the boundary of the right side, this downward oriented term. And these 2 line integrals, let me erase the distractions here, ignoring all this other stuff. These 2 terms are on the same curve with opposite orientations, and they cancel. And likewise for all the other new edges that we've introduced, right? So I can go through and let's see, what about this edge here? Well, I'm going to have one that way and one this way, and they cancel. And what about on, let's see here, this edge right there? Well, one that way, and they cancel. All those interior edges are going to cancel. Now, there are some terms that don't cancel. For example, this edge right here. Right? When I look at the sum of the boundary circulations on the parts, this is one of the terms. And, there is a term coming from, being part of the boundary of this piece up here. There is nothing down here for it to cancel with, so that doesn't cancel. And likewise, that one doesn't cancel with anything, and that doesn't cancel with anything. And likewise, coming from the other direction, these also don't cancel with anything. So all that remains is exactly as it should be, the circulation on the boundary of the original hole. Yeah?
Is that just the way you set it up?
Yeah, that's right. It's a consequence of the convention that we made about boundary orientations.
Okay.
Right? Yeah, exactly. So, in some sense, what's the motivation for having this sort of weird rule about always with the region on your left? It is so that this will work out exactly like this.
Okay.
Yeah. Very carefully planned. Yeah, that's right.
I just want to make sure.
Yeah.
That, how do I call it? Like differential D, if I could call it like that. Like the one with the differential symbol.
The little partial symbol.
Boundary pieces, right?
Yeah, this notation here means boundary.
Okay.
Yeah. That's right. Yeah. Cool. Okay. So boundary circulation is an accumulating quantity. Now, I'm going to try to make a case here that this allows for thinking of boundary circulation in a certain way. I find this to be really helpful. I feel like there is a red herring, a sort of a wrong way of thinking about things that we are sort of naturally drawn toward, and that is, let's talk about boundary circulation and where is boundary circulation, and very naturally we tend to think of it where it's computed, namely on the boundary right? But very importantly, we want to think of boundary circulation as being something that we associate to the region itself. Now, we don't compute it on the region itself, but it is what we get from looking at the region itself. After all, it is the region itself that we are chopping up into pieces, right? And so we should think of each piece of boundary circulation as being associated to the piece of area that it comes from. So here's a related note. Let me ask a seemingly silly question. Here is a boundary circulation. Now you'll notice I'm deliberately looking at this in what I'm trying to encourage you to think of as being the wrong way to think about it, right? But how much of that boundary circulation is happening there? How much of the purple boundary circulation is happening where the green boundary circulation is being measured? And the answer is, well, what are you talking about? They don't even touch each other. They're completely different curves. They don't intersect or nothing, right? But again, that's just the wrong way to think about it. It's just much more natural to think of it this way. Looking at this whole region, if we want to talk about its boundary circulation, looking at this region here, if I want to talk about its boundary circulation, and how much of the yellow boundary circulation would you naturally say comes from the orange boundary circulation? And you'd answer this the same way you would answer any other question about an accumulated quantity. Just look at it and see, right? So as I've got the numbers drawn on here, apparently the boundary circulation for the whole is 33. And the boundary circulation for this orange area on the inside is 6. So how much of the 33 comes from the orange? Well, 6. It's not a weird question. It's, the whole is the sum of the parts. This is one of the parts. So however much of the quantity comes from that is how much of the quantity comes from that is what it is. So again, don't conflate where something is computed with what it's associated to, and you might say where you think of it as actually being. Okay, so I want to encourage the idea of thinking of boundary circulation as being in the interior. It's sort of distributed through the interior, and you can just measure it based on where you're measuring it. Okay. All right. So now here's another related idea. Again, we're just laying groundwork at this point. We haven't really concluded anything. We don't have any punchlines or theorems yet, right? Related idea, though. Here's something we've done with accumulating quantities. We've talked about density. And so, for example, I could take a little piece of area, like that little piece of area right there, and I could ask, how much mass is there in that piece of area? Nothing weird about this question. I'm talking about mass per unit area all the time, right? Quantity per unit size. That's what a density is. Specifically, we restrict our attention on this sort of thing to accumulating quantities so that we can talk about, for example, how much mass is in that little piece. You need to be able to talk about where something is, to be able to talk about how much is in that location. Okay, so mass per unit area, big surprise. We call this mass density because the accumulating quantity is mass. All right, so I'm going to now take this same idea and apply it to this new accumulating quantity. Looking at this little thing down here, right, there's a certain amount of area in there, and we can talk about this accumulating quantity called boundary circulation. And in that region, there is a certain amount of boundary circulation. It's an accumulating quantity, just like mass is. It has location, just like mass does. You can talk about how much boundary circulation there is for that piece, just like you can talk about how much mass there is in that piece. And so if you've got quantity per unit size, again, you can call that a density. So this is what we're going to call circulation density. And we call it circulation density because the quantity in question is circulation. Boundary circulation, to be specific. Okay, now, this is a creepy idea, right? This seems a little sort of like, I thought this was supposed to be stuff, right? Like mass or, some sort of physical quantity, right? Every time we've talked about a density before, it's been a physical quantity. It turns out you don't need for it to be a physical quantity. All you need is for it to be an accumulating quantity. And the idea makes perfect sense. A little new, right? A little bit sort of geometrically unfamiliar, but it totally holds water. Okay. All right, so this idea of circulation density is going to be very useful, very important as we develop these ideas coming up. So again, that's what it is. Quantity per unit area, circulation per unit area. Thus the name circulation density. The formula for it turns out to be this right here. Now there's a calculation that's needed to actually demonstrate this. That, given a vector field P comma Q, I would need to actually compute the circulation, right, on that boundary. Sure, right, that's because it's boundary circulation, literally. So you'd have to compute that circulation, compute the area, divide, take a limit as size approaches 0, and that's just a calculation. It's totally doable. It's in the book. I'm not going to go through it here because it's a bunch of details. I think in my opinion, the most important thing, especially for engineers, most of y'all are engineers, to take away from this is not the details of the calculation, but the interpretation, how do you visualize this, right? What are the, morally, what are the big ideas that come together to make this happen? And to me, it's not the details. To me, it's this idea of accumulation, the idea of orientations, and the idea of this density. So take a look at that calculation if you'd like, but you don't have to. This very often gets called curl. It's fine, I guess. Rote, I think is a little in certain ways a little better. The rote here is short for rotation. I like to call this Green's operator because it's going to turn out that this is, in fact, exactly the integrand of the big theorem we're about to write down called Green's theorem. Right? So it's literally the operator used in Green's theorem. So I think Green's operator is very natural. And related to that, I like this little notation here as well, GRN. It's not very common, but I find it satisfying. Our textbook, on a few occasions, uses this notation. I really don't care for this. I'm going to say I dislike it enough to give it a frowny face. It is out there. There is a case to be made, but it really is actually pretty awkward. In fact, if you look at what this expression is literally saying, it makes it look like you're doing a cross product, which is a peculiarity of 3 dimensions. We're not in 3 dimensions, we're in 2 dimensions. So I don't really think that's a thing in our context. I think this is very misleading and confusing. So I encourage you not to use that notation, but do be aware of it because you're going to see it, for example, in our textbook here and there, and probably in other places as well. Okay. All right. So with all of that settled, we are actually now ready to motivate, I don't want to say derive, but to give a motivating argument for Green's theorem. And it's just a matter of putting together the ideas that we've already talked about. Okay, so the first thing we talked about was this idea of circulation. You start off thinking of circulation as being an expression, that it's a formula that you compute. I am pushing, of course, this idea that it's actually kind of a quantity. And when you have a quantity, when you have a kind of a stuff, it makes sense to give it a name. Right? So I'm going to use the lowercase Greek letter sigma to represent how much circulation. Okay. Next, we have argued that this is an accumulating quantity. The whole is the sum of the parts. And again, that's pretty literally what I've got written down here. When it comes to circulation, the whole total amount of circulation is the sum of the parts, right? That's really exactly what this says, right? So the fact that circulation accumulates gives us that green equation. And then lastly, we've talked about density, specifically circulation. A little piece of circulation is circulation per unit area times area, right? Rolls off the tongue very naturally. You might think of it as the areas cancel, right? Take a pick. So specifically, that thing right there, circulation density, computed by that formula, pick your favorite of these notations, that's the thing that goes here to relate d sigma to dA. And guess what? We're done. We have our new theorem here. Here it is. That integral is equal to that integral. Circulation accumulates over the interior, and therefore is a double integral of circulation density. One way to think about it. And this is called Green's theorem. How we doing? Everybody all right? Okay, so now, of course, you might not you might not come at this from the point of view of circulation. You might just find yourself looking at a line integral at some point, and if you're looking at a line integral, well, hey, if everything sort of fits together, then you can take a question about a line integral and rewrite it as a question about a double integral with a new integrand, and sometimes the subsequent double integral is easier to compute than the original line integral. Not always, but sometimes. And when that works out, this is awesome. All right, let's see an example of that in action. Here we go. We have ourselves a curve, C. We have a vector field, F. And we are being asked to compute this vector line integral. Now, first observation I'm going to make about that example. It does not announce itself as being a Green's theorem problem. It just says compute the vector line integral. So you get to decide for yourself which of your many tools in your toolbox you want to pull out to address this problem. You could just plug and chug on this. You parameterize the unit circle. That's not hard. The vector field doesn't look so bad, at least not at a glance. You could just say, you know what, I'm just going to plow forward and plug and chug on this. Let me try to explain why I think that's a really bad idea in this case. It's a really bad idea in this case. What happens when you parameterize the unit circle? X and Y become trig functions, cosine and sine. That means this is going to become e to the power of cosine t. That's a weird term to have to deal with inside of an integral. Even worse than that, you're going to have tangent of sine of t. That's super weird to have to deal with inside of your integral. I got to say, I'm not looking forward to trying to compute that integral. Everybody see? So brute force plug and chug is a bad plan, at least so it appears at a quick glance there. Okay, so let's try to use our shiny new theorem. Here we go. After all, our theorem says line integral, and I can compute it with a double integral. So cool, let's try to do that. But wait a minute, we do have to be careful. There's a condition looking right at us here that we have to worry about. It's subtle, it doesn't leap off the page, but it's very important. That's this right here. Very importantly, this theorem does not say, hey, here's a formula for computing any line integral at all. this only applies to boundary line integrals. It has to be, your domain has to be a boundary. Right? That's intimately part of the argument that we made to justify this result, was that it was a boundary. Right? So now you might think to yourself, okay, well, come on, I'm just going to go ahead and punch it up anyway, even if it's not a boundary. Well, here's the problem. Only if your region is a boundary can there be a set that it is the boundary of, and this set that the curve is the boundary of is the domain for the new integral. So if your curve is not a boundary, there is no D on which to even talk about a double integral, much less conclude that it's the same as the line integral. Did everybody see that? That's a nasty little sticky wicket, right? If your curve is not a boundary, there is no region on which to do your double integral. So it's an instant crash and burn. Nothing works if your curve is not a boundary. So that's what we need to worry about first. Let's look at the question and ask ourselves, is our curve a boundary? And let's be careful about this. There it is, clockwise oriented unit circle. Goes all the way around, of course. I just don't want to mess up my picture, but oriented clockwise, as indicated in the statement of the question. Is this a boundary? No. Remember, boundary, loaded word. The orientation business with the word boundary is very, very important. This is oriented the wrong way. So, not a boundary. Can't use Green's theorem. Out of luck. Everybody see the bad news there? Now, this is fixable. Not such a big deal, in fact. Let's look at this other curve here. Now, that's the same exact curve. It's still the unit circle, just that now I'm going to orient it the other way. When I orient it the other way, of course, it's not the same. This is the same underlying curve, opposite orientation. But this C minus is a boundary. Right there. Right? C minus, counterclockwise oriented unit circle, is literally the boundary of that disk D. Yeah. Is that cool? Everybody good?
Then why is the clockwise one not?
Because the word boundary means counterclockwise.
Oh.
That's the thing. Yeah, so everything's very delicate and rigid. And yeah, the word boundary means, well, it means as you go, the region's on your left, but in this case, it would mean counterclockwise. Yeah. Yeah. Okay, so what are we going to do about that? Okay, so we've been asked to compute the clockwise oriented line integral. Instead, I'm going to compute the counterclockwise oriented integral and just fix it with that minus sign. Again, that's what an orientation change does. An orientation change just gives you a minus sign in your result. And now that we've translated the question to being about a boundary, right? Now that we're looking at literally a boundary, now I can invoke Green's theorem, and Green's theorem tells me that this boundary circulation is a double integral of Green's operator. So Green's theorem does kick in. You just have to kind of fix that boundary orientation issue first. It's satisfying. Okay, so it's all downhill from here. Let's see here. We have to compute Green's operator. Here is our vector field F. The formula for Green's operator, of course, is back here. It is right here. dq dx minus dp dy. Be careful with this. It's not about the letters of the alphabet, right? When I say q here, I mean the second coordinate of your vector field. When I say p here, I mean the first coordinate of your vector field. So x partial of the second coordinate minus y partial of the first coordinate. And that makes for a pretty easy calculation here. Oh, whoops. There we go. the x partial of our second coordinate is just 3. The y partial of our first coordinate is just 1, so 3 minus 1, 2, nice constant. The result then is an awesome double integral that's just an integral of a constant over a well-known shape and easy to compute, and there's your answer. Okay. Is everybody happy? Okay. All right. Okay, another example. Another line integral I want to compute, right, like so. How are we going to compute that line integral? My curve is a collection of 4 line segments. That between the two of them makes kind of a triangular figure 8, like I have figured there. Okay. And how would I compute that line integral? Well, now, again, the sort of brute force, if you want to just take a deep breath and plug and chug, you could do that, but there are 4 separate line segments. You'd have to do 4 separate integrals, each one of which would be reasonable, but it remains 4 separate integrals, and all else being equal, we probably don't want to do that. Okay. All right, so here's the clever move. I'm going to take these diagonal line segments, I'm going to rewrite them by chopping them in half. So I'm going to take that first diagonal and chop it into 2 pieces. I'm still going to be covering the exact same ground, right? Likewise on the other one, this I'm going to rewrite as that pair. And then all together, the entire 4 line segments is now 6 line segments, like that. And the nice news, though, is that this left half is literally and exactly a boundary. Orientation and all, right? This trio of blue outlined line segments is exactly the boundary of D1. Now, the other ones, no such luck, right? If I look at that and that and that, between the 3 of these, I mean, it is kind of, it's the border of D2, right? It's going the wrong way. It's oriented backwards. So what I can say is that what I have is just the opposite orientation of these 3 line segments, which is, in fact, exactly the boundary of D2. So again, it's just a matter of recognizing with a superscript minus sign that what we have here is just the opposite orientation of an actual boundary. Yeah.
So like when the question says the line segments from 0, 0 to 2, 2, you're assuming that the flow is also from 0, 0 to 2, 2. Or to be told that.
No, the vector field whose line integral we're interested in computing is this thing right here. So I have a totally different formula for the vector field. The vector field doesn't really have it. You have to keep in mind there's a domain and there's a vector field, and they're independent of each other, right? So in this case, what the vector field is, well, we'll get to that later.
I guess like what I'm asking is, how do you know that like the arrows are pointing the direction that?
I got you now. Okay, I misinterpreted your question. You're asking, how did I know that from 0, 0 to 2, 2, how did I know that the orientation was that way? As written, it says from one to the other. That just the language just implies that orientation. Is that what you meant?
That's what I was asking.
I got you now.
So
All
like
good.
If we were given a photo, we should just assume that we draw like the arrow from the
Sometimes there's a million ways to phrase things in language, right? Language is a little sloppy sometimes, but sometimes the language, I'm going to say, implies an orientation. Yeah, that's right. So you do have to read and interpret carefully from how the question is written. Yeah, exactly. Okay, so we're in business again. C is one boundary plus the opposite of another boundary. So I'm going to rewrite C as that boundary plus the opposite of the other boundary. I'm going to recognize that an orientation problem gives you a minus sign, right? When you switch the orientation the other way. And now we have ourselves two boundary circulations. And boundary circulations can be computed with Green's theorem. Is that good? Everybody all right? Okay. And again, now we're just a hop, skip, and a jump away from being done. Green's operator turns out to be 9. That's just a couple of partial derivatives, easy to compute. Point being that that's a constant. Integral of a constant over a region is just constant times the area. And very conveniently, in this case, get this thing to cooperate, the area of D1 and the area of oh gosh, I wanted a different color there. The area of D2, pretty clearly the same, and so 0. Is everybody happy with that? Did everybody see how the little details kind of fit in at the end there? So way easier, I think, than computing 4 separate integrals is just to realize that even though it's not quite a boundary, you can relate it to boundaries. And once you have it in the language of boundaries, Green's theorem crushes everything else. Okay. All right. Moving along. Here's a nice twist on Green's theorem. This is clever observation. You'll notice that what I'm going to start with right here, this is really just an application of Green's theorem. Right? I have boundary circulation on the left, double integral on the right. I am applying Green's theorem to this specific vector field, 0, x. Right? Free country. This is the one I want to apply it to. Now, why am I applying Green's theorem to this specific vector field? Because it's a special vector field. It's not uniquely special, but it's a special vector field. And what's special about it is Green's operator is just not only a constant, but Green's operator is 1. And I like 1. Right? As an integrand, 1 is awesome. It's not as nice as 0, but it's a pretty cool integrand. And that said, in this case, with an integrand of 1, of course, all we're actually computing with this double integral is just the area enclosed, right? The area of that region D. Okay, so what we've got then is because we applied Green's theorem to this specially chosen vector field, we have a line integral that will compute areas. Right? Normally, if you're going to compute an area, you would sort of expect that to be a double integral or maybe a single variable integral where you look at cross sections or something. Here we have a line integral that computes area. It seems like a magic trick, but it's really just Green's theorem applied very, very specifically. Okay, now, how do people tend to write this result? Don't forget that this is dx comma dy, and you can just straight up crank out that dot product, and that dot product, 0 times dx plus x times dy, would just give you integral x dy. And I've said before that most cases I don't really like this coordinate notation. I like the vector notation better. I find it sort of easier to relate to. It's the objects in here are geometrically natural, sometimes physically natural. What's going on with this is a little mysterious, right? But in this case, you gotta give it its due. It's significantly more compact than this notation. So in this case, I think it's really kind of, case can be made anyway, kind of better. So altogether then, this coordinate line integral computes area. Okay, now we're going to do an application of that in just a moment, but before I do, I want to develop another sort of neat trick, and that is this right here. This is just a computation. In fact, this is I a 6.1 style computation. You can just straight up plug and chug on this. And of course, now we're going to have to parameterize our straight line segment, L here, starting at one point, ending at another point. That's a Chapter 1 parameterization problem. You want to make sure you can do that. Right? Once you have it parameterized, you can plug in directly and compute that line integral. And here's what I claim you'll get. Your line integral on that straight line segment will always be the average value of x times the change in y. And it's just nice how convenient, and I think convenient is a pretty good way to leave it. This is a very convenient answer to compute an entire line integral. Okay, but now of course, this second result here only works for a straight line segment only. Okay, so altogether though, we can put these together, and specifically, we're going to apply that in just a second to compute this area down here, the area of this monstrosity. What an ugly thing, right? And how would you normally compute this area? Like if this were a high school geometry class, how would you compute this area? I guess what I could do is I could break this thing up into various little triangles. I could slice it like that and that and that and that and that and that. And I believe I've counted that would be 7 separate little triangles, and I could compute the area of each one of those triangles and add them up. But here's the problem. Most of these triangles are not right triangles. What's the formula for computing the area of a non-right triangle? You'd need to know the height. I would need to be dropping perpendiculars all over the place in sort of arbitrary directions. There'd be a tremendous amount of geometry that would go into computing these areas. A tremendous amount of inconvenient geometry. That's a really, really hard high school geometry problem. Right? So I'm going to argue using the above two tricks. First of all, our special case of Green's theorem tells us that I can just compute the area as a boundary coordinate line integral x dy. The boundary, of course, you can see from the picture, is just a sum of a bunch of line segments, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 line segments. Right? So I've got to go over the whole boundary, but it's just 9 separate line segments. And on each individual line segment, for example, let's look at that line segment. On that line segment, per that formula up there, integral x dy on that line segment, just the average value of x times the change in y. And this is just easy arithmetic, right? There's a fair amount of it, right? But it's integers and convenient fractions, right? No square roots, no trig. You can imagine the sort of horrors that you would imagine coming up if you were looking at the triangles themselves, and you would expect square roots to come up from looking at lengths, right? And you would imagine trig to come up from when you're dropping perpendicular. It could get real nasty. This arithmetic here is just convenient. So let me show you, again, putting this into action. Let's look one edge at a time. I'm just going to do just the first one, looking at that first edge. Let's see here. The average value of x, well, x starts at 1 and ends at 12, so the average is 6.5. That was easy. Right? What is the change in y? Well, y started at 1 and ended at 6, so the change in y is 5. And therefore, computing the line integral on that edge with that formula right there, 13 halves times 5 is 65 halves. Repeat for the other 8 edges. Super easy arithmetic. Add them up. There's your answer, 19. Right? Turns out to be nice and easy when you add it all together. Everybody see how that works? It's real clever, super clever. We're using a powerful idea, multivariable calculus idea of Green's theorem applied very cleverly to crush a high school geometry problem that would be brutally unfair in a high school setting. All right. Okay. All right. So I want to get started on this last bit before we call it a week. So let's talk about flux through a curve. Y'all remember from chapter 3 we talked about flux through a surface. And the idea was that if you have a flat surface, and we've so far only considered flat surfaces, if you have a flat surface and if there is fluid flowing through the surface, and if you know the velocity of the fluid flowing through the surface, then you can ask the reasonable question, well, how much volume of fluid per unit time is going through that surface? So in other words, given a velocity, what is the flow rate? Right? So here we're going to do just a two-dimensional version of that. Instead of a surface, I have a line segment. Instead of a three-dimensional fluid flowing, I have now just a two-dimensional fluid flowing. Those are all supposed to be the same vector. And, if there is a two-dimensional fluid flowing, I can talk about the quantity of fluid per unit time passing over that line. Right? Now, I claim that the punchline on this, the answer, is going to be that this expression right here, F dot n times the length L, that is what answers the question for you. And where did I get this from? Well, you're going to notice right off the bat it looks an awful lot like that chapter 3 formula for flux. Right? It's just that now this is a length instead of an area. Right? So it's pretty believable, I think, just sort of superficially. But you can also demonstrate this formula. I think this is a nice exercise. You don't have to do it, obviously, but I think it'd be if you're in the market for a practice problem, look back at what we did in chapter 3 to motivate the three-dimensional version of this and adapt to this two-dimensional setting. It's arguably easier than the three-dimensional, the 3D example we did in chapter 3. And if you adapt the argument, follow it through, this is what you'll get. Okay. All right, so what we're going to entertain here now is a harder question. Instead of a straight line segment, let's suppose I want to talk about a curve, not just a curve, but a curve that is a boundary of some region. Right? And as usual, I'm not going to draw the whole entire region. I just want to focus on, just a part of the boundary. So the actual boundary goes around and, comes back around and stuff. And how would I compute the entire boundary flux through the whole boundary? And again, by the way, there is another convention here. This is another arbitrary but standard convention. When you're talking about flux, the standard interpretation of boundary is outward. Arbitrary convention. Totally arbitrary, but extremely standard and therefore, required. Okay. All right, so this is something that we can chop up into little pieces again. If you have your entire curve like that, you can look one little piece at a time, and on any little bitty piece of curve, that's approximately straight. Not exactly, but pretty close. It's approximately straight. It has length ds. On that little piece, I can say that flux is just the formula on the previous page. F dot unit normal vector, outward, times the length, and that little length is ds. And then, of course, I add up over the entire curve. Now, the problem is that when I write that down, now this is just a chop it up, add it up argument, but when I write that down, I find myself in the awkward position of needing to compute this kind of integral that I don't know how to compute. Right? How do we compute an integral of something dot in ds? We've never seen that before. This is not a regular vector line integral. we don't really have experience with computing the unit normal vector n either. So we're kind of up a creek, sort of. So this is where this little geometry argument up here is very handy. If you have a vector field and a normal vector, just a kind of a neat observation that you can rotate both of them 90 degrees. Linear algebra tells us what you get when you rotate p comma q. You get minus q comma p. And geometry tells us what happens when you rotate a normal vector. If you rotate a normal vector, you get a tangent vector. Perpendicular is perpendicular to tangent. Right? So, having made that observation, I'll now point out that, well, that means that this dot product and this dot product are the same, because when you rotate a pair of vectors, you're not changing the magnitudes, you're not changing the angle between them, because we're rotating them both the same amount. So the dot product doesn't change at all when you do this 90-degree rotation. So f dot n is f perp dot t. And just a quick bit of foreshadowing, that turns our integral that we don't know how to deal with because of that n ds into an integral that we do know how to deal with because, of course, TDS is dx. So it all turns into something much more familiar. We'll finish the rest of this next time. Y'all have a good weekend. See you on Monday.